Welcome to Another Explainer. Today, we're taking abstract molecular chemistry and transforming it into high-stakes clinical medicine. This is the chemistry of survival, from molecule to bedside. You know, every single breath you take, every single time your heart beats, your body is managing this incredibly delicate microscopic chemical balance. We're going to dive deep into how the human machine actually works under the hood to maintain this equilibrium. By the end of this explainer, you're going to completely understand the invisible life-or-death battles happening inside you every single second. Here is our roadmap for the breakdown. 1. The chemical foundation. 2. The defenders. 3. The breaking point. And 4. Counterattack and medical hacks.
All right, let's jump right into section 1, the chemical foundation. We are looking at water, pH, and protons. First things first, we have to establish that water is not just some passive container in the body. In medicine, water is an extremely active reactant. Thanks to its high dielectric constant, water dissolves ionic substances by actually orienting its own molecules around them. It creates what we call solvation shells. And these shells literally dictate osmotic pressure and fluid shifts in patients. For example, this is exactly what causes the severe swelling you see in a patient with edema. But to understand the real stakes of human survival, we have to step back and ask why we even use the pH scale in the first place. You've probably heard of pH, right? But why is a pH of 7 exactly 10 times more acidic than a pH of 8? Well, it all comes down to how we measure hydrogen protons. Pure water actually has a slight tendency to undergo reversible ionization. This means a water molecule literally splits apart, giving us a hydroxide ion and a solitary hydrogen ion, which is really just a free-floating proton. Now look at this impossibly small number, 0.0000004 moles per liter. Believe it or not, that is the actual baseline hydrogen concentration floating around in your body right now. Working with a number that incredibly tiny is an absolute mathematical nightmare, especially if you're in a fast-paced clinical setting like an ER. So to make those numbers manageable, we rely on the logarithmic pH scale, but we have to deeply understand what a base 10 logarithmic scale actually means. It means the scale is not linear. Every single drop of one whole number in pH doesn't just add acidity, it multiplies the proton concentration by 10. So a pH of 6 has 10 times the hydrogen protons of a pH of 7, and literally 100 times more than a pH of 8. So here is the absolutely crucial point. Venturing outside the strict arterial blood limits of 7.35 to 7.45 is catastrophic. Now, your intracellular pH is slightly more acidic, usually between 6.7 and 7.0, because of constant cellular metabolism. And your gastric juice? Highly acidic, down around a 102, which helps denature proteins so you can digest your food. But your arterial blood must stay in that incredibly tight 7.35 to 7.45 window. Why? Because if your blood pH drops below 6.8 or rises above 7.8, the physical shape of your biology just breaks down. Proteins begin to denature. Their complex, folded, three-dimensional structures physically unravel. And when that happens, the enzymes powering your cells stop working, metabolic pathways completely shut down, vital cellular machinery collapses, and death occurs shortly after. To prevent those fatal limits, our bodies have to manage acids and bases perfectly. In clinical medicine, we define these chemicals purely by their proton-moving capabilities, using the Bronsted-Lowry theory. It's elegantly simple. An acid is a proton donor. Think of it as a microscopic game of hot potato where the molecule desperately wants to give a positive hydrogen proton away. A base, on the exact opposite hand, is a proton acceptor. It acts just like a catcher's mitt, ready to grab that free proton right out of the fluid. And this brings us to a really vital distinction. Physiological chemistry is entirely dominated by weak acids. Strong acids, like hydrochloric acid, dissociate completely in water. If you drop them in, they aggressively and explosively give up all their protons, all at once. You absolutely do not want that happening in your bloodstream. Weak acids, like lactic acid or carbonic acid, only dissociate partially. Their behavior is governed by the pKa principle. Basically, a lower pKa signifies a stronger acid. The real magic rule here is that when the pH of the surrounding environment exactly matches the pKa of the acid, that acid is exactly 50% dissociated. Half of it is holding on to its proton, and half of it has let it go. This partial dissociation is the absolute secret to survival. It allows the acid to absorb chemical shocks rather than acting like an explosive charge. Let's move on to section 2, the defenders. These are your biological buffer systems. Before we look at the specific defenders, we need to define what a buffer actually is. A buffer is a system that actively resists sudden changes in pH whenever small amounts of acid or base are introduced. It usually consists of a weak acid and its conjugate base acting together like microscopic shock absorbers. And that brings us to the Henderson-Hasselbalch equation. I know it looks like some heavy math, but listen, this is the absolute most important equation in clinical acid-base physiology. It calculates the exact pH of a buffer system. It tells a doctor precisely how the balance of a base and an acid determines the pH of a patient's blood. If the concentration of the base goes up, you can see mathematically how the pH will rise and become more alkaline. If the acid goes up, the pH drops. By utilizing Le Chatelier's principle, which in plain English just means a chemical system will always shift to balance out any new stress you put on it, these three distinct buffer sponges soak up or release protons second by second. First, the bicarbonate buffer. This is your primary blood system. It's an amazing open system controlled by both your lungs and your kidneys. Then you have the phosphate buffer. This one operates mainly inside your cells and in your urine, where the local pH is a lot closer to phosphate's ideal pKa. And finally, protein buffering, specifically hemoglobin inside your red blood cells. Get this, as hemoglobin releases oxygen to your tissues, it literally changes its three-dimensional shape. This shape change turns it into a fantastic proton acceptor, helping to sponge up the dangerous acidity that gets generated when your blood transports carbon dioxide back to the lungs. All right, let's look at section 3, the breaking point. This is where we get into clinical acid-base disturbances.
So, what happens when that physiological fortress is under constant acid attack and the microscopic shock absorbers finally fail? Well, doctors analyze a patient's breaking point using a test called arterial blood gases, or ABGs. They reference this exact set of normal values to diagnose where the disturbance is coming from. They check the overall pH to see the baseline balance. They look at PCO2, which represents the physical gas pressure of carbon dioxide dissolved in the blood. They measure HCO3-, representing the dissolved bicarbonate ions. And finally, they calculate the anion gap.
Based on those ABG numbers, any deviation from the normal pH is strictly classified as either a lung problem or kidney problem. A respiratory origin is driven by carbon dioxide gas. For example, say a patient hypoventilates due to an opioid overdose. They essentially stop breathing effectively. Because of that, CO2 gets trapped and builds up in the blood. Thanks to Le Chatelier's principle, that massive excess of CO2 physically pushes the chemical buffer equation to the right, forcing the creation of more and more hydrogen protons until the blood turns highly acidic. On the flip side, a metabolic origin is driven by bicarbonate. This happens when the body loses its basic buffers, like through severe vomiting or diarrhea, or when it accumulates non-volatile metabolic acids that just eat up all the available bicarbonate. Now, to pinpoint the exact cause of a metabolic acidosis, doctors use the anion gap formula. You take the measured sodium concentration, which is a positive charge, and you subtract the measured chloride and bicarbonate, which are both negative charges. Why do we do this? Well, the human body must always maintain electrical neutrality. The total positive charges literally have to equal the total negative charges. If we subtract the primary negative ions from the primary positive ion, and we get a gap larger than the normal 8 to 12 range, it means that electrical neutrality is being maintained by hidden or unmeasured negative acid ions lurking in the blood. This gap is the diagnostic holy grail for figuring out if a patient is being actively poisoned from the inside. If that anion gap is abnormally high, we rely on the Mudpile's mnemonic to neatly organize and identify the massive amount of potential toxic culprits. We're looking at methanol, uremia, diabetic ketoacidosis, propylene glycol, iron, lactic acidosis, ethylene glycol from antifreeze, or salicylates from aspirin. For instance, in diabetic ketoacidosis, or DKA, a severe lack of insulin forces the body to burn fat so rapidly that it floods the bloodstream with highly acidic ketones. Or take lactic acidosis. When tissues are starved of oxygen, they rely on emergency anaerobic metabolism, turning out massive amounts of lactic acid. Running through this diagnostic checklist narrows down exactly what disease or poison is attacking the patient in real time. And we constantly have to anchor this underlying chemistry back to the patient's vital signs. Why? Because the body's frantic attempts to fix the pH can actually create entirely new, lethal problems. When severe acidosis hits, the body desperately tries to hide those excess hydrogen protons by shoving them inside the cells. But to maintain that vital electrical neutrality we just talked about, a positive ion has to leave the cell in exchange. That ion is potassium, so the body effectively trades one fatal problem for another. Severe acidosis shifts massive amounts of potassium out of the cells and straight into the blood. This causes a visible and incredibly deadly disruption to the patient's heart rhythm known as hyperkalemia, which can lead straight to sudden cardiac arrest. Let's wrap things up with Section 4, Counterattack and Medical Hacks. This is all about compensation and drug delivery. Let's see how the body counterattacks and how we as medical professionals can actually hack pH to save a life. Listen, the body never lets a pH imbalance go unanswered. If one system fails, the other attempts to restore that golden 20-to-1 ratio of bicarbonate to carbon dioxide, and it does so using specific biological timelines. Step 1 is incredibly fast. The brainstem senses the acidic pH and instantly triggers deep, rapid Kussmaul breathing. The lungs can physically blow off that acidic CO2 gas in a matter of minutes. Step 2 is slow. The kidneys take a solid 2 to 4 days to fully ramp up. This is because they can't just exhale a gas. The kidney cells have to undergo complex cellular metabolism to actively synthesize fresh bicarbonate and forcefully secrete hydrogen protons out into the urine. Now, let's look at a true medical hack. Understanding exactly how buffers work allows doctors to manipulate drug delivery through a brilliant concept called ion trapping. Most drugs are weak acids or weak bases. A fundamental rule of human biology is that lipid cell membranes, think of the blood-brain barrier or the gut wall, are highly nonpolar. They strictly repel anything with an electrical charge. Because of this, only unionized, meaning non-charged drugs can actually cross those lipid membranes. Once a drug gains or loses a proton and becomes ionized or charged, it gets violently repelled by the membrane and becomes totally trapped in whatever fluid compartment it's currently floating in.
So how do we actually use this to save a life? Well, imagine an aspirin overdose. Remember the S in mud piles stands for salicylates. Doctors will intentionally alkalinize the patient's urine by giving them an IV of sodium bicarbonate. Aspirin is a weak acid. By pushing the urine pH up and making it basic, we are actively weaponizing the Bronsted-Lowry theory. The basic urine literally rips a proton right off the aspirin molecule. This turns the aspirin into its ionized, negatively charged form. Because of its brand new charge, it is now strictly repelled by the kidney's lipid membranes. It is completely trapped in the urine. It cannot be reabsorbed back into the bloodstream, which means it dramatically accelerates its own excretion and flushes safely right out of the body.
It really makes you appreciate the invisible molecular battle happening inside you every single second, doesn't it? Next time you take a deep breath, I want you to picture the chemistry we just went over and ask yourself, are you just taking in oxygen? Or are you actively blowing off CO2 to save your blood from turning into acid? The chemistry of survival is happening right now, keeping you perfectly balanced. Thanks so much for joining me on this explainer, and keep learning.